Hello everyone, and welcome to part 1 of my tutorial series on working with the KITTI Odometry dataset with Python and OpenCV. So we're going to be playing with the KITTI dataset. You can see this is their website here. I'll have a link in the description of the video. And you can see that they've got a whole lot of different datasets here for performing different tasks that are related to autonomous driving. So specifically, we're going to be playing with the odometry dataset, but let's take a little look at their preview video here. Got some nice dub reggae going in the background. Alright, so that's enough of that. You get the idea. So basically they have sequences of images where they've driven a car around and taken pictures and also taken other sensor readings like with LiDAR or whatever they're using for these particular tasks. And basically these are benchmarks. So they're collecting this data so that research teams can then, take the data and then try and get the best results possible. So if we go over to the odometry data set here, you can see this is where you download it. You're going to need to do that if you're going to follow along with this tutorial series. And then so you've got all these submissions here from various research teams, and they've got, their results. And so anyways, in this series, what I'm going to do is we're going to try and apply some basic computer vision principles of structure from motion and do visual odometry with this data set. And so what they've given you is stereo pairs of images. So here they have grayscale, which is mostly what you need to do visual odometry, and they have an RGB set of cameras as well. And then you get Velodyne LiDAR scans, point clouds, and you can see these are pretty big files, but storage is cheap these days. So get an external hard drive, go grab these things. And I mean, really, this is just a cornucopia of data to play with. If you're, a data scientist or a roboticist or somebody who's aspiring to work in the autonomous vehicle field, you really can't beat this. You can see this came out in 2012, and it's still being used as one of the #1 benchmarks for this kind of task. I don't think they have dates right here, but anyways, yeah, I mean, you read papers, and they're still using this data set to prove their methods. So it's a great thing to have. So we'll be playing with the odometry data set. And so let us take a quick look at the video of the sequence that we'll be looking at, which is the first one, because of course you would. And go full screen. All right, so this is the first sequence. It's at 10 frames per second, so it's a little jumpy, but that's the speed that they were triggering the camera, because I think that was the same frame rate that the Velodyne scan completed a rotation. So you get one LiDAR point cloud per image set. And so this is the left camera, and it's black and white, and then they've got a stereo pair for each frame. So let me go back over here. And if we go over here to the setup, let me see this. All right, so this is where they give you the schematic of how their sensors are set up on the car that they drove around. So you can see there's two actual stereo pairs of cameras. You've got cam 0, the left grayscale camera, and that's where this coordinate frame is based. And then this is the right grayscale camera, and then the RGB cameras are a separate set that sit just to the left of those. And then the Velodyne, the LiDAR, sits right behind the left grayscale camera. And so we'll use this in a second, but this series will be a few videos because it's going to take a while to really kind of cover everything that you need to know in order to do this kind of thing. And in this video, I'm basically just going to do more covering the fundamentals of computer vision so that you know what you need to know, and in order to do what we're going to do. Because I'm assuming, people watching this video that you are like an intermediate Python programmer, that you do know how to program in Python, because we can't go over all that. and also that you know how to do some linear algebra, like matrix math and that kind of thing, because you know, and you may not have to, like, as I go along, if there's something you don't understand, just pause the video and go. The internet is a fruitful place for tutorials on this kind of thing. I really recommend Khan Academy if you need some help with fundamentals of matrix math, calculus, whatever. I mean, he's got videos on almost everything, and he explains it really well. So if you get lost, just pause the video, go over to some other site and figure it out, because they'll be able to explain it better than me. But so anyways, we are gonna go over in this video the fundamentals of computer vision that you need to know. So if you're already, familiar with computer vision, you can feel free to, go ahead and skip to the next video where we'll actually do some coding together. But my advice is, a little review never hurt anybody, so stick around. And because if you know the subject well, then maybe you can, if I get anything wrong, you can let me know. And that would be great, because I'm trying to learn too. And that's really kind of the reason I put this video together, because as I'm learning this, there's not a lot of very candid explanations of some of this material. A lot of the times you end up, to figure this stuff out, you have to read through some pretty dense stuff. So I was hoping that by doing this video that I could save somebody some time, because if this video had been available when I was learning this, then, maybe I could have gotten there a little quicker. So anyways, let's get into this. So this is the Jupyter notebook. I'll have a link in the description of the video, and it's at this GitHub repository here. So I recommend you go, you fork it, you clone it, and this is, some sample images that we'll be getting along the way here, and our final result, which you can see is a little bit of a mess, but you'll see that this is actually a really hard thing to do. So, just doing it with like some basic principles, this result's actually not that bad. But really, in practice, people are using extremely complex systems to do this, where, and I'll get into all that. But anyway, so let's go over here. And so let me just load these packages. In the next video, I'm actually going to code through all of this kind of stuff with you, but this video is going to be mostly just kind of pointing to pictures and explaining how this works. So I'm going to load my packages anyways, so that I can work with code if I need to. And so you can see here, I've loaded the ground truth poses. So, all right, let me cover this. This notebook is going to assume that you've cloned this repository into a folder that also contains the data set. And so let me show you what that might look like here. All right, so you can see this is my folder. It's called Odometry, and I've got my data set is here in a folder called Dataset, and then this is the folder of the repository. So if you want to use the notebook without having to modify the file path, set it up like this. And with your data set, you have poses and sequences. And when you download the data from the KITTI website, if you use WinRare to extract it into your folders, it'll automatically merge all the files where they ought to be. And that's a lot easier than trying to do it yourself. So definitely use WinRare. That's the way to go. So anyways, back here. So we got the ground truth poses loaded up into this using pandas, because you could do it without pandas, but why wouldn't you? And so got it loaded up. We can see that the shape is 4541 by 12, and so there are 4,541 frames in this one sequence. And I think there's 11 sequences in the odometry data set. We'll just be working with the first one, and that's 00, as you see here. And so in this one sequence, they've got 4,541 frames. Each frame is going to have a stereo set of images. So one picture from the left camera, one picture from the right camera. And then these are the ground truth poses. And so you can see there's 12 columns, and that's because they've flattened out 3x4 transformation matrices. So if we take the first row of that data frame that I've loaded up here and reshape it into a 3x4 NumPy array, then we can actually see what this looks like. And I've rounded it just so you can see it easier. And you see, basically we have a identity 3x3 matrix stacked horizontally with a 3x1 translation vector. So what is this telling us? This tells us that at the very start, what these arrays tell you is where the camera is at that time step in reference to the global coordinate frame. And what am I trying to say? In practice, the global coordinate frame is the first position of the left camera. So they establish your global coordinate system, which, you know, because really when it comes to a global coordinate frame, like one is as good as any. So they just start it on the first camera position of the left camera. And so the left camera in the first position is in its own coordinate frame. So you have a rotation matrix, which is an identity matrix, which means it isn't rotated at all. And then you have a translation vector of 0 because it hasn't moved yet. And then if we were to take the next row and look at that, we can see that it still hasn't rotated, but it's moved. And it has moved a little to the left, a little upward, because as we'll go into, the y-axis points downwards. And then it's gone forward because the z-axis in camera coordinates goes away from the camera. And we'll cover all this. So basically what I was just talking about, this is RT. And so it's a 3x3 rotation matrix, and it's a 3x1 translation vector. And this is how far you've moved X, Y, and Z, and this is how much you've rotated with respect to the global frame. And so basically you take this matrix and then you multiply it by the X, Y, Z coordinates of the camera, and then that'll tell you where you are in the global coordinate frame. So for instance, let's take, for example, this first position. I'll go ahead and save it as, or assign it to a variable first pose equals that, and we will keep it up there, first pose. And then, so in every frame, as the camera moves, the camera's origin is always 0, 0, 0 in its own frame. So if we wanted to know where the camera is in the second frame in regards to the global coordinate frame, which is the camera's frame when it starts, then what we would do is we would take the origin of the camera, which we could set as numpy array of 0, 0, 0, xyz 0, and then 1. And you have to put that 1 there because that makes the matrix multiplication work out. They call that homogeneous coordinates, which we'll talk more about in a second. But just for now, remember that in order to make this math work out, you have to put a 1 and make it a 4D vector. And then we would say first pose dot with origin, and then this will give us where the camera is in the global coordinate frame. And so we see it gives us, basically it's the same as this translation vector here. So you really don't even have to do this. You can just look right at this translation vector and that'll tell you where the camera is in the global coordinate frame. So if we were to, just for fun, make first pose actually the second pose, but take a look at it, then this is where the camera is in the second frame. We'll change that back to stay consistent here. Anyway, so that's that. And so that's how they're tracking the motion of the vehicle. And when you're estimating the position, that's the format that you're going to keep your estimates in, and the format that if you were to submit it to them, you would have it and that they would expect it to be in. They're not really taking submissions from just like, independent, people. They only take them from like research teams, and there's a good reason for that. But, we're here, we're learning, we're having fun. That's what this is all about. So I've got an image here that shows us what a camera coordinate frame really kind of looks like. And we can see that the X direction goes to the right, the Y direction goes downwards, and the Z direction goes directly out of the center of the camera. And so, you know, you just got to keep all this kind of in your mind as we go through this, because, you know, if the car moves forward, then you're going to expect to see a positive Z value. And if the car goes up, it'll be a negative Y value, and left and right are kind of as you would expect, positive X, negative X. Now, the reason that they point Y in the negative direction is twofold. One is because this keeps it being a right-hand rule coordinate frame, because if you know the right-hand rule, basically if you were to stick your thumb in the Z direction, then your first finger is X and your middle finger is Y. It's kind of hard to see the way I did that, but, you know, try it out for yourself. If Z was like, you know, this, then X would be that way, and then Y points back at me. Anyways, you know, Google it. And also it makes it convenient because if Y is in the negative direction, then it lines up with the way that you count pixel locations, because here you see pixels are the variables for them are U and V. And so if the Y and X point in the same direction as U and V, which are counted from the top right, or sorry, top left corner of the image plane, then it kind of just like makes more sense intuitively. So those are the reasons for that. And so this is a very useful picture because it shows you how there's a point out here, a 3D coordinate that's in reference to the camera frame, and then it gets projected onto a flat plane at Z equals F, so the focal length away from the camera. And so it becomes any point that's out here can get projected onto a flat surface. And you do that by dividing by the Z value. We'll go into that in a second. It gets a little weird, but basically when a camera sees something, it sees a flat image, right? And because all a camera sees is data. So all the depth information is essentially lost when you get a picture of something. And you have to figure out how far away things are, and that's exactly why they have a stereo set of cameras, because you can measure what they call the disparity between the two cameras, and then that allows you to reconstruct the 3D positions of things that are in the two images based on how far they've moved from one camera to the other. Sort of just the same way your eyes measure depth is what they're going after here. And you need that depth because a single image, you know, they've got ways of estimating depth now with neural networks, but stereo, like classic stereo depth, is still holding its own with those methods, and it's computationally a little simpler than using neural networks to do the same thing. So it's still widely used. Good thing to know how to do. So that's what we'll be doing, especially because they gave you stereo images to do this with, so that's what they intended. Okay, so I'll go ahead. This code here, I'll go into the, you know, actually coding this out in the next video, but you get the ground truth all into an array here. And then we can look at what the actual ground truth looks like as the car moves forward. So that's kind of ugly. So what we need to do is we need to position it so that we're looking the way the camera looks, which is with the Z-axis pointing forward, the Y-axis is negative going upward, and the X-axis is standard, you know, negative goes to the left, positive goes to the right. And so this is what we're looking at. This is where the car went. You can see it took a bunch of corners, it doubled back over itself in a few places, and yeah, and it's on a bit of a hill, which looks rather intense in this rendition, but it's because, excuse me, the scale of the Y-axis is different than the X and Y, so it wasn't really on a giant hill, it just looks like it. So anyways, a useful thing to know if you're doing this kind of thing, which I'll also cover in the next video, is that this is using Matplotlib in notebook mode, which you can do by running this command here. And it's really useful because you can turn things and look at them and stuff. It has a major problem if you do inline before notebook, but for some reason, if you do notebook and play with this, and then do an inline later, you'll be able to switch back and forth. If you do inline first and then notebook, it's not going to work, and you'll have to go back and reload everything to get it to work. So that's a good thing to know, little trick. Anyway, so here's the first image of our sequence from the left camera. And okay, so projection matrices. So in the dataset file, they give you a calib.txt file, which is the calibration information for the sensors. And you can see here that there are P1 through, or I mean rather P0 through 3, 4 Ps, and then a TR. And, you know, the thing that you should always do is, hold on one second, is you should read the README file that comes with the data set. And this will tell you all about what's in there. It's not as explicit as it could be, but it's there. And so we'll scroll down here and we'll find that the calib.txt file has calibration data for the cameras. P0 and P1 are 3x4 projection matrices after rectification. This is an important thing to keep in mind. And P0 denotes left, P1 denotes the right. We saw that actually in the schematic image that I showed you before. And TR transforms a point from the Velodyne coordinates into the left rectified camera coordinate system. So that's what you need if you're going to take points from the point cloud of the LiDAR scans and put them into the coordinate system of your left camera, which we will need to do. And so, you know, I encourage you, if you get the data set, read the README. It's always enlightening. So, give me one second. All right, so one thing to note is that when I downloaded the data set and I got the calib.txt file unpacked and in the data set, I loaded it and it only had these rows and it didn't have the TR, the translation, or rather transformation matrix to the Velodyne LiDAR. And so I actually had to Google around a bit to get the proper link to get the calib file that does have this row. So I don't know what happened there. Must have been some something happened with them. But anyways, for your convenience, I have included the proper link to download the right calibration file here. And so if you go to GitHub, get this repository, it's a cornucopia of information. And this is the link that you need in case your calib file did not come with this row. And so what are these projection matrices? Well, the projection matrix of a camera is as so. We look at P0, it's here, and this is what it looks like. It's a 3x4 projection matrix for the left camera in this case because it's P0. And it has information here that at the moment may not be particularly easy to understand because it's actually a combination of two matrices for the camera, which are the intrinsic matrix and the extrinsic matrix. The intrinsic matrix tells you the focal length of the camera in the X and Y direction, and it also tells you where the image center is on the image plane. I'll go into that more in a second, but anyways, so this is basically what a projection matrix does, is you have P, here's your projection matrix for your camera, and then you have X, Y, Z coordinates in the global coordinate system. So in this notebook and through this tutorial, X, Y, Z in the global coordinate system will not have a subscript. They're just X, Y, and Z. Later, if I have X, Y, and Z in the camera coordinate system, I'll have a subscript of C so that you can tell the difference. But anyways, and realize that there's a 1 down here, which means that these are homogeneous coordinates. And all that means for now is that you just plug a 1 in below the Z, and now you've got homogeneous 3D coordinates. And like I said before, the reason they do that is because your projection matrix has 4 columns. And so if you're going to dot product that with this, you need the 1. And essentially what the 1 is going to do is it's going to add the translation vector components to whatever the rotation matrix does to the X, Y, and Z. And so it works out, math works out nice, and that's why it's there. So you take an X, Y, Z 1 homogeneous 3D coordinate in the global frame, take the dot product with a camera's projection matrix, and then that's going to put you into pixels you V, which is X, Y, and 1. So these are also homogeneous. And you notice that there's this lambda out here. And this is what they call the scale, which means that in order for the two sides of this equation to be the same, the pixel homogeneous coordinates need to be multiplied by the scale. So more clearly written, we can move the lambda over to this side, and you see that this is all being divided by lambda, and then you get nice clean pixel coordinates, and they're homogeneous. So we'll get back to lambda in just a second. So this is what a projection matrix actually is. You remember I told you that it's a combination of two matrices. It's a combination of K, the intrinsic matrix, dotted with RT, which is the extrinsic matrix, which is a transformation matrix. It's a 3x3 rotation matrix horizontally stacked with a 3x1 translation vector. I realize for some of you, you're like, duh, but it's, not everybody. Sometimes a little bit of review, and this video is kind of aimed at people who are getting into this and want to play around. So if this is rudimentary to you, skip ahead, go to the next video, whatever, but I'm going to cover it. And so this is what a projection matrix really is. It's K is the intrinsic matrix of the camera, and that we'll go into this, and then R is a 3x3 rotation matrix, and T is a 3x1 translation vector. So keeping that in mind, we can plug that back into this equation here, and this is what's happening. And so, all right, so we need to remember that in the README file, it said that these projection matrices were after rectification. So what that means is that actually the projection matrices don't correspond to the different cameras. They translate points in those cameras' coordinate systems into the coordinate system of the left camera. So that's kind of the opposite of what a projection matrix usually is, because usually a camera's projection matrix takes points in the global coordinate frame, and then it puts them into the coordinate frame of that camera. But these rectified projection matrices, they're not actually doing that. They're taking points in their own coordinate frame and putting them into the coordinate frame of the left camera. So it's basically the opposite thing. And so it's a very important distinction to make here, because if you're going to go about doing math with these things, you need to know what they're doing. And so remember that. But we'll go about, I'll distinguish between the two. So if we look at this math more specifically, and this is why I like to look at it like this, because when you just look at a projection matrix, the projection matrix, like in this equation, it takes 3D coordinates and puts them directly into pixel coordinates, which is, it's an all-in-one step. And that's cool, and it's all very, bundled up and clean, but sometimes it's helpful to think about this stepwise and what's really happening. And so R and T are going to take these 3D coordinates in one frame, in the global frame in this case, and they're going to move them into the camera's frame, and they'll still be 3D coordinates. And so that's what a transformation matrix does. So this is the transformation matrix, and for a camera it's known as the extrinsic matrix, same thing. And it's going to put these 3D coordinates and move them into the camera's coordinate frame. Then K is going to convert that into your pixel locations. And so it's a two-step process. First, you move from the 3D world of the global coordinate system, you move into the 3D world of the camera coordinate system, and then you change that to be pixel locations on the image plane that sits in front of the camera that you're talking about. And so, yeah. And so remember, your camera coordinate system, Z points forward, X points to the right, and this X here means that Y points into the page or downward. Right, so we can see that there's a measurement here of 0.54 meters between the left and right cameras of the stereo pair. And so let's see what we got. So you remember I told you that the projection matrix can be decomposed into the intrinsic and extrinsic matrices of a camera. And so OpenCV, known as CV2 in Python here, has a useful function, decompose projection matrix, that does that for you, and it'll spit out a intrinsic matrix, rotation matrix, and translation vector, as well as some other stuff that we won't worry about, but you need to put these there to catch them. And so let me, I really wish I had a copy of this because I'm messing with my thing here. So let me make a copy real quick. Bear with me. So yeah, it's going to take a second. It's kind of a big file. I really encourage you to get this repository and read through all this, because I took a lot of time to really break all this down. I'm trying to explain it. When I was going through and learning all this, I was really hoping that there would be like, some dude on YouTube that would just be like, all right, man, so here's what's going on. And there really wasn't. So I decided I'll be that dude. So here I am. So let me go ahead and reload my notebooks. The reason I'm doing this is because that other notebook is the actual notebook from the repo that I want people to read. So if I start messing it up, I don't want to have to go back and undo all my changes. So, oh, gone too far. No, I haven't. All right, and here we go. So let's take a look. So what this does, like I said, it breaks you out into the intrinsic, rotation matrix, and your translation vector. And so there's a little bit of math here that isn't explained, which I probably should be explaining. So what we're going to do is we're going to split it here, and we're going to run this. And then we're going to take a look at T1, because remember I said this was going to be a 3D translation vector, so you would expect it to be XYZ. And we look at it, and well, let's round it because that's really hard to look at. Round 4 places. All right, so here we have it, and you'll notice that it's 4D. So what happened? Well, it's homogeneous, and the thing is that if you want to understand this in 3D, you need to set the fourth value back to 1. And you do that by dividing it by that value. So we'll say divide, well, T1, let's do it like this, T1 divided by T1, the fourth value, which is 3, and then we'll round that to 4. Yeah, see. Now this is actual 3D XYZ. Because if that last value isn't 1, then you haven't scaled it properly and you're not looking at the right thing. So that's why down here you see that I've just done that, and then we print out the matrices here. So this is the intrinsic matrix of the camera. And so what this contains is the focal length in the X direction, focal length in the Y direction, and then this is the image center in pixels. And so I'm going to go much more into detail on that in just a second. And then that OpenCV function, it breaks the rotation matrix and translation vector into 2 separate things. So if you want to turn them back into a 3x4 transformation matrix, then you're going to need to use np.hstack, which horizontally stacks them back together. And so you put a list in R1, which is the 3x3 rotation matrix. T1 is the translation vector. And so we've already set T1 equal to its divided by its own fourth coordinate, so that it's back in 3D homogeneous form. And so you can't stack a 4D vector horizontally with 3x3 rotation matrix. So we're taking T1 up to that fourth value, which we don't need anymore. And then so let's take a look at that once we do. If you don't know that nice little trick, it's Control-Shift- to split your cells so that you can look at output in between. So let's actually look at it. All right, well, also that is disgusting to look at, so we'll round it to 4 places. And there we go, nice and pretty. All right, so here we have a transformation matrix, and this is of the right camera because we use P1. So look here. we see 0.5372, which is in meters. And so what's that? What is that telling us is that this camera is 0.54 meters to the right of the left camera, exactly as the schematic had told us, except that there's an issue here, because if this were the extrinsic matrix for the right camera, then that means that the origin of the left camera would be negative 0.54 meters because it's over to the left. And so if we take points in the global coordinate frame of the left camera's origin, which is 0001, and then we dot it with this transformation matrix, then we see that the x value is positive 0.54, which this is exactly where the distinction between a rectified projection matrix and a regular camera projection matrix differ, is because this transformation matrix is not describing the right camera. It's actually describing, it relates things in the right camera's coordinate frame to the left camera. So it's actually a projection matrix of the left camera, treating the right camera as a global coordinate system. It's a little confusing, but you know, it's the opposite. So that's what this means. So it's important to make note of that, because it kind of tripped me up for a little while. Anyway, so yeah, rectified projection matrix. And so anyways, I'm gonna go more into this in the next video because we don't need it right now. Let's get more into some theory here. Right. Okay, so this is talking about, here I've replaced the transformation matrix with an identity transformation matrix, which means this is what happens if you're going to take a point in a camera's own coordinate system and then project it into the pixel coordinates of that camera. Then you don't need a rotation and translation, because the 3D point that you're considering is already in the coordinate frame of the camera that you're talking about. So if you're doing that, then this is really the equation you end up with. The RT has just disappeared because we're already in the coordinate frame we're talking about. And then you see I've put XYZ camera here, and notice that this isn't a homogeneous coordinate vector, because K is a 3x3 matrix. And so actually, once you have multiplied your transformation matrix by your homogeneous coordinates, you end up with a 3x1 vector, because there's 3 rows in the transformation matrix, and then K is then dotted to that, and K is a 3x3 matrix. So this is what we're looking at here. And so this is that lambda I was telling you about, that you have to divide all of this by lambda in order to actually get your pixel coordinates. So what is lambda? Lambda is Z in the camera frame. So they just divide everything by the depth. And what this does is it projects everything onto a flat plane that is Z equals 1 away from the camera. And you can think about this very intuitively, because imagine you're in a completely dark void, right? And there's a glowing, image in front of you that, it's like a super HD television. And if you're in a completely dark void, and you see this square image of mountains or something, you don't know if it's really far away from you and gigantic, or if it's closer to you and very small, because you don't have any point of reference. And so this is essentially what the camera's doing is projecting things onto a flat surface that's conveniently Z equals 1 away from you. So if you're looking at me, the Z axis is coming directly at me from you, and let's say you have a point that's 3 toward me, 3 to the right, and 3 up, and you want it to stay in the same place visually, then you would, if you have Z equals 3, then you would just divide it by 3, and it's going to stay basically in the same place but closer to you. And my hand gets bigger, but think about just a single ray of light. All these rays are coming out of the camera, and so if you divide everything by the depth from the camera, then everything shrinks down to right in front of the camera, but it actually stays in the same place on this flat image that you're looking at. And so they're doing this because, you know, we're talking about an image as a 2D thing. And so you basically just lose all depth information, and you map every ray of light coming into the picture as a flat plane z equals 1 away from the camera. And so then, so that's what lambda's doing. And so I actually rewrote it here is, you know, z, it's all being divided by z of c, or sub c, which is, you know, z in the camera coordinate frame. And then k, which contains the pixel information, gets multiplied into your now flattened image, and it turns it into pixel coordinates. So, you know, remember that. Everything's being divided by c. So I'm going to go back to this image now and, you know, take a minute to look at it. So this point will get divided by z and put onto a flat plane that's in front of the camera. Now, you might notice that I told you that we were going to put everything on a flat plane that was z equals 1 away from the camera, that we get by dividing everything by z. And we are going to, except that in this image, z equals f, which is the focal length in meters that the camera actually has. So why am I talking about z equals 1? Well, it took me a little time to figure this out myself, but I'm going to go through it step by step because we want to get intuitive with this thing. So anyways, here's a picture of old-timey picture of a camera obscura, and this is where all the math that we're using is sort of derived from. And so in this picture, the focal length f is going to be the horizontal size of this room from the hole to the wall that this guy's looking at. And so that is where the image becomes in focus. And so it's called the focal length. And so that's a useful visualization. And so here's the same kind of thing. You know, we're going to take this slide from Robert Collins of Penn State. Thank you very much, Robert. It's going to be x equals the focal length. Well, okay, so little x and little y. These will be the x and y coordinates of a point that's projected onto that flat plane that I was telling you about. So we distinguish by calling them little x and little y because they're on this plane that is a distance f away from the camera. And we'll get to why it's 1 in a second. Because, and this is where it's all derived from. There's similar triangles rule where you have your y over z, which is your actual depth from the camera, is the same as little y over f. And so you multiply the f back to this side, and this is how you get little x and little y. And so looking down here, I've rephrased it as little x, little y, and f are equivalent to f over zc, which is lambda, being multiplied by your 3D vector, or your 3D point in space. Okay, so the secret is that this is actually the formula that's being used here, which is that it is f over lambda or f over zc, but they're actually canceling out the f here. And the reason that they're doing that is because you're probably wondering, like, well, how can you get away with multiplying this side of the equation by 1 over f and not this side? Well, the secret is that the K intrinsic matrix actually contains f, but measured in pixels, but not for the z. And so what you've actually done, so imagine this is all canceled out, and then we're going to divide x, y, and z by lambda, which is in meters. So these are in meters and lambda's in meters. Then once you have divided by lambda, you're in unitless measurement. And so you don't have meters anymore, you just have numbers. And then you're going to multiply by k, which has focal length measured in pixels. And then that's going to take you from unitless into pixels. And so you are where you want to be. And so basically this is just handy because you don't have to worry about the focal length until you get here. And so, and you know, when we're talking about 2D images, so this would work. Remember I said once you divide by lambda and you're not multiplying by f. So, you know, let's just think about this for a second. If we go back up here, if this fellow starts measuring points on the wall, he's going to be measuring them in units, in meters, you know, for instance, and not unitless measurements, which is really just like a mathematic artifact. And so in real life, you would have this image be in meters, but we're just taking an extra step here to where we're canceling the meters out and then reapplying our focal length in pixels and then, you know, getting here. And so really this is secretly what's happening, but you don't really have to worry about it if you just know the formulas. But for me, it really helped to get that intuition down, because essentially you can think about it like this, which is where if we shrink, you know, everything down by dividing it by its depth onto a flat plane in front of you, and then if we shrink it down even more and move it closer to you, then it really just stays the same size because it gets closer even though it's smaller, but all the information is still there. You've just increased your DPI, but all the information is still there. And so we don't need the convention of keeping it in meters. We just, you know, divide and then multiply back by pixels. So I think I've covered that enough, but it kind of tripped me out at first, but there you go. So also we have CX and CY in the intrinsic matrix, and what these represent are the image center in pixels of the image plane. So what does that mean? That means that a ray of light coming directly down the z-axis into the camera is going to land at these pixel coordinates. And so, well, you might be thinking like, wouldn't that just be the center of the image? And you'd be wrong, because it turns out that a lot of cameras don't align the very z-axis with the center of their sensor, and so a ray of light coming down the z-axis is actually going to hit a little off center on most cameras. So that's why it's important to calibrate these things, because if we start projecting points onto a pixel coordinate system and we don't know where the center of the image is in relation to the coordinate system, then we're going to project them into the wrong place. So we can, you know, run this cell here. You'll see that the actual center of our image is at 620.5 by 188 pixels, and the optical center so that's the term I should have been using, optical center, is at 607 and 185. So it's a little to the left and a little above, because remember, pixels are counted in the vertical direction downwards. And so, yeah, it's just a little off center. But it's important to know that, because if you're going to start taking points in 3D and mapping them to a pixel coordinate, then you need to know how to orient this thing. So that's where that information comes in. And if you really think about, you know, I broke this down because, you know, I think that it's getting pretty explicit in this rendition here, but, you know, sometimes it really helps to just see everything right in your face. So you can see that what we've done is we've divided everything. X, Y, and Z are getting divided by ZC, and then X and Y are getting multiplied by the focal length in pixels, and then they're having the optical center in the X and Y direction added to them. And the reason that, you know, if we'll just think about this is, let's say you have, you know, a negative X location, and then you scale that to a flat plane in front of the camera and then multiply it by the amount of pixels, then the 0 on the x-axis is in the center. And so if you have a negative x value, you add the center of the image in pixels to it to make sure that the very left of the picture is at 0. And so it offsets the origin of the pixels to the top left corner, so that 0, 0 is up here, whereas 0, 0 for x and y is in the center. That's what these are doing. All right, so that's that. now we know everything that we need to know. That's the fundamentals of camera matrices, projective geometry, and a very, very basic look at computer vision. And so I think that we're going to end the video there, because in the next video, we're actually going to start coding, and we're going to create this dataset handler class to start playing with our data from the KITTI dataset. I hope you found this video informative. If you have any comments, corrections, anything like that, please leave them in the comments. I will have links to some reference materials as well as the GitHub repository in the comments or in the description of the video. So make sure to check those out. Clone the repository so that you have the Jupyter notebook and you can read through it. Check out some of the references that I put in there. And yeah, I will see you next time.